welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. This week we are discussing about the hard and soft magnetic materials. Mostly we are discussing about the advancement along the direction of magnetic materials. Both the materials should be more and more harder, and one of the very important criteria that tells us whether the magnet is very hard or not hard, that is the corrosivity. Now, on the other hand, people are developing the second class of magnetic material, that is the soft magnetic materials, that has a very low corrosivity value. So, in both the direction there are large number of developments. So, last two classes we have mostly focused on the fundamentals of magnetism, and we have cited couple of example and the metallurgical aspect in terms of microstructure of several hard magnets. We will continue that discussion also on today. So, like neodymium iron boron, the second class of high energy hard magnetic material is basically samarium cobalt, and here there are several composition which has been discovered, like 1:5 ratio, and here it is 2:17 ratio. The typical characteristic of a hard magnetic material is analyzed by the demagnetization curve, means the energy required to demagnetize a hard magnet is the basic characteristic of a hard magnetic material. So, here this is represented by B into H, okay, max. So, the maximum value under this curve, okay, which is represented here. So, in this side this is B, that is basically the magnetization, and in the x axis it is the applied field. So, here it is kilo Oersted is given. Now, if you kindly have a look, you will see that this is the typical representative demagnetization curve of neodymium iron boron, whereas the lower corrosivity one is 217 and the 1:5 samarium cobalt that has almost the highest one. Okay. So, this is definitely one of the hardest magnet. So, the typical microstructure has hexagonal crystal structure, and the BH max value is quite high among all the other hard magnet, that is 160 to 170 kilojoule per meter cube. So, this is a very high value. Now, if you look at the microstructure, how these hexagonal grains are present in a microstructure. So, here this is a high resolution transmission microscopic image, and the length scale is 5 nanometer only. So, the interesting feature here that this is in the length scale of, let us say, 10 to 15 nanometer size grain. So, we have nanocrystalline hard magnet, and that has such kind of very high BH max value. So, means the energy required to demagnetize. On the other hand, the second composition that I have shown you here, that is 217, that also have very fine scale structure as the samarium cobalt 5, and here samarium cobalt 5 that separates region in this 217. So, 217 like a average composition, and we have bands of 1:5 crystals in the microstructure. So, that is why it has a lower corrosivity value. because single phase material many times are very difficult to process because of their mechanical properties. Also they have some property called magnetorestriction. So, because of that, when we apply a magnetic field, there is a length change occur in a material, and because of that length change or the strain, so material may loses its other properties. So, the typical processing technique that is involved with processing of such hard magnet, that we can go for melting casting route, and then we crush the powders, okay, to produce a very fine particle size. Like melting casting cannot give you, let us say, like 5 nanometer size homogeneous microstructure, that is very difficult to achieve. So, we may get such kind of 10 micrometer size crystal size. Now, then each particle that consists of let us say single crystal 1,5 phase, and then these powder need to be aligned under a magnetic field, and so that there can be a easy axis of magnetization, and all the particles that should be parallel to the applied field, and then these particle put in a compression die, so that we compact those powders. Okay. So, usually the alignment and compression that are done in a sequentially in the same apparatus, and this alignment means I am talking about the magnetic alignment actually. Okay. So, the domain are in the particle, they are aligned and along a particular direction. So, the compressed powder is then sintered at a temperature around 1000 degrees centigrade to make the final magnet. So, this is a typical processing route of samarium cobalt hard magnets. Now, there must be some principle or very underlying physics of improving this corrosivity value, and they should be discussed today. So, how do we choose a different element to produce a hard magnet and make it more harder? So, these fundamental principle can be explained using basically Bethe-Slater curve. So, here what we plot actually the interatomic distance by the diameter of the 3D electron shell. So, the ratio is plotted along the x axis, and in the y axis we plot actually the exchange energy. Okay. Means if I have only one type of atom present in a crystal, and if I bring another atom of different type close to each other, then whether the magnetic exchange or because of the coupling is going to increase or decrease. So, this is basically the fundamental aspect of this discussion. So, exchange energy that depends on the balance between the Coulombic interatomic force and the kinetic energy. So, if you look at different elements and their phases, they are basically lying in this. So, means the interatomic distance for a gamma iron is different than the BCC iron. BCC is the alpha iron, and gamma iron is, we call it as a austenite, or let us say the pure gamma iron, that could be. So, we can add let us say cobalt or some other element like nickel or gadolinium, okay, or manganese or chromium. So, whether the whole exchange energy is going to increase by addition or decrease. So, that is basically the point of interaction. Now, if we think about various types of magnetic materials like diamagnetic, paramagnetic, if we apply a magnetic field, the material does not respond too much. So, whether you are going to add some other element, so the net exchange coupling is not going to change too much, but exchange coupling can be very effective if the material itself is a ferromagnetic. Okay. Let us think about a pure alpha iron, okay, and then we are adding let us say cobalt into it. Okay. So, then we can calculate basically these the interatomic radius as well as the 3D orbital shell diameter, and then we can estimate that thing. So, here usually the top side is for the ferromagnetic element and the anti-ferromagnetic part is in the bottom side. Okay. So, that is why the schematic is shown here that with the opposite side in nature. So, for ferromagnetic, anti-ferromagnetic and ferrimagnetic, we can think about to make some sort of exchange coupling for the benefit of making a more harder magnet. So, in that case there are two different type of atomic exchange mechanism has been seen. Okay. So, here we are not talking about the exchange coupling between two grains, we are talking about the atoms, we are talking about the exchange interaction between two atoms. So, let us say I have one atom which is iron, another atom is the cobalt, like that. So, the direct exchange mechanism and the indirect exchange mechanism, these are the two mechanisms that people have observed, and in case of direct exchange, this exchange are short range coupling, means when they are very close to each other. So, the coupling is very strong and it is in a short range because of the ferromagnetic ions. So, this is a short range coupling between two ions, and the example here, so like in case of ferromagnetic material like iron, cobalt and neodymium iron boron. So, all the spins are parallel and the atomic moments that will add up. So, we can enhance the magnetic properties. Now, there are indirect exchange where it also is very strong or dominant, and the long range interaction here in metal which has some without having let us say overlap between neighboring magnetic electrons. So, this is the indirect exchange when two atoms we are talking about coupling in a relatively longer length scale. Okay. So, like we have a ferrimagnet where I have iron, two different types of ion, or let us say barium ferrite, and also in case of anti-ferromagnetic material like such as cobalt oxide or manganese fluoride. So, they are characterized by two different sub lattices with two different opposite moments. So, that we know, because if I have two different ion, then there is a net value of those two ion that basically provides us whether they are anti-ferromagnetic materials or not. So, this amount basically that ferromagnetic reduction or anti-ferromagnetic absence of a net moment. So, this Breth-Slaughter curve explain us about adding another atom in a lattice and improving whether ferromagnetic properties or anti-ferromagnetic material with the hard magnetic properties or the corrosivity. Now, from the samarium cobalt discussion, we have seen that there is definitely some benefit of making materials in the nanoscale in terms of magnetic property enhancement. I am talking about the hard magnetic property enhancement. So, nanoscale material definitely we have elaborately discussed in the earlier weeks. So, we all know that if I have such kind of very small grains, then I have mostly 50% of the area that is covered by the grain boundary fraction, where atoms are not positioned in the lattice, and there are some benefit because of the more number of surface atoms. So, here the close to the constituent particle that may alter the domain size. So, what I am talking about, I have some magnetic domains, and magnetic domains has some typical size, and if the grain size is very large, then the domain size may be the smaller than the grain diameter. What I want to mean that in a single grain there could be two domain, means in those domains atoms, the magnetic spins are aligned along a particular direction. But if I keep on decreasing the grain size, then I may reach to the domain size, or maybe if the grain size is too small, then in a single grain I have single domain. Okay. So, that I am talking about. So, here the higher portion of the atoms that are present in the surface or interfaces, and also we have some broken translational symmetry of the nanoscale grains that result some reduced coordination number and broken exchange bonds. So, that may interact because of such kind of high fraction of grain boundary atoms. So, this is the grain boundary atoms. So, the magnetic property may be changed or altered or may be tuned. So, for producing such kind of nanostructured hard magnet, there are some processing methods that has been people observed, that is hydrogen decomposition and desorption and recombination, HDDR process. This is also very sophisticated technique. Also melt spinning. So, these are ribbon shaped material, or let us say thin film by some deposition technique, chemical synthesis. So, we will discuss all these detailed different techniques in the next week, when we will discuss about advanced processing technique. But nevertheless, I should mention that these are the very important technique for producing such kind of hard magnetic materials with a nanoscale microstructure. Now, for nanostructured magnet or let us say exchange coupled hard microstructure, means hard magnetic microstructure, three major types of microstructure has been classified. So, if you have a look to the left hand side, I have shown you first one is the exchange decoupled magnet. So, the most important terminology here, the decoupling, means I have one magnetic phase and the other phase which is a non-magnetic phase. Okay. So, this is a non-magnetic phase. Here these are the domain which is aligned along this particular direction, and here it is in the some other direction. So, you can see these are let us say some random orientation of the magnetic domains in a exchange decouple, where the matrix, this white color phase which is a non-magnetic in nature. Okay. Here also we can achieve a very high coercivity value. So, as an example like 217. Okay. So, here I have some 217 with some nitrogen that are some crystallite of 500 nanometer size are present. Now, on the other hand, this is a nitrogen of 3, and let us say for a single phase material where we do not think too much about the grain boundary phase, but let us say in case of neodymium iron boron with 20 nanometer size only grain size, and these are the magnetic domains that are aligned along a certain particular direction, and here also we can achieve very high remanence magnetization. Now, we can think about mixing these two type of microstructure, and where both the phases will be magnetic. However, one will be relatively harder than the other one. So, we can produce some nanocomposite, means I have nanoscale grains, and in nanoscale grain I have two different grains that has a exchange coupling between let us say relatively harder and relatively softer magnetic nanograins. So, in that case we can achieve both higher corrosivity as well as high remanence. So, in a exchange decoupled magnet we achieve basically high corrosivity, whereas high remanence is a feature in case of a single phase material. So, in case of nanocomposite we can achieve basically both the properties. So, this is important, and let us say in case of neodymium iron boron we have some alpha iron grains. So, that has such kind of two phase two different magnetic domain, hard and soft, and we can achieve that. In case of samarium cobalt with a cobalt phase is present. So, with addition of gadolinium or iron we may have some cobalt or iron phases present, or let us say for iron platinum, which is also a very hard magnetic phase, and we have some alpha iron present in it. So, this is one of the very typical example where we can improve both coercivity as well as the remanence. So, let us say if I think once again about such a plot, and then this is basically the remanence and this is the coercivity value. So, we can achieve both. So, for high coercivity material, or let us say the energy product, then this BH max can never exceed it. It has been observed that mu 0 into m r square m r square is this one divided by 4. This is a typical let us say observation that the scientist has observed, that we cannot go beyond such kind of values. And now, in case of exchange coupled hard magnetic material, I have shown you 3 different types of microstructure, and the major aim here that I have basically one hard phase and another one is a soft phase, and to make a nanocomposite with a exchange coupled hard magnetic material. The example here I have schematically shown you that in one case I have a hard magnetic material with a low value of the remanence, okay, whereas I have a very high value of coercivity. Now, in a softer material I have a very high value of remanence m r or b r, and here this is the m r which is low, and this is basically the m c, that is the coercivity. So, here coercivity is almost very less, but I can design a microstructure by let us say these 2 type of nano phases, and the resultant microstructure will give us a higher m r as well as higher m c. So, this is basically the aim of the development of such nanostructured hard magnet. And the exchange coupled hard magnetic material, the microstructural variant, that the combination of hard and soft magnetic material that produces a new hard magnetic material, okay, with a significantly higher remanence, that is the m r here, and the coercivity, which are essentially unchanged. So, you can see the coercivity does not change here, but I am getting basically a higher m r. So, that produces that will give us a during demagnetization we will get a larger area under the curve, which is the B h max. So, higher B h max can be produced. So, yes, we have several examples. I would like to show you. So, these red color domains are the hard magnetic domains. Okay. So, these are hard magnetic material, and the green matrix is the soft magnetic material. Now, they are randomly oriented, random aligned hard magnetic particle. However, we can optimize the structure with a aligned hard magnetic particles in such a way, and we can produce a resultant such kind of exchange coupled hard magnetic material. And so, here I show you some microstructure in a nanoscale. You can see actually these are very teeny grains, even something in the scale of 5 to 10 nanometer. We have some Fe3O4 and Fe iron platinum. Here iron platinum is basically one of the soft magnetic phase that are present here as a 2 phase, and the second case here in the B case I have iron platinum domains and I have iron 3 platinum domains, which coexist basically just nearby. So, this is also another such kind of exchange coupled magnet or hard magnetic nanocomposite. So, there is enough experimental evidence that people have developed such kind of hard magnetic material by combining 2 different phases. Both are harder, one is relatively more harder than the other one, and they have a exchange coupling, and by mixing that kind of nanocomposite microstructure we can achieve such a very high B h max values. Now, is it all time that if we reduce the grain size the benefit will be there or not? So, that may be another question. So, please have a look at how the property or magnetic property changes in a nanocrystalline material. So, like here I have a 6 nanometer grain size, I have 13 nanometer, I have 23 nanometer in case of a samarium cobalt nanoparticle. So, here people observe that in 6 nanometer the behavior almost similar like basically amorphous material. Okay. So, where it is so soft that the coercivity value is very low, and if you plot coercivity versus particle size, it keep on decreases, okay, almost reaching close to 0. Whereas, in case of a 13 and 23 nanometer particle, you can see that there is a finite value of the Hc. Now, similar Hc or the intrinsic corrosivity we can plot with a particle diameter. Okay. So, particle diameter increases along that direction in a log scale. So, here I have basically let us say 1000 angstrom or let us say 100 nanometer. In this case it is 10 nanometer and here and here it is 1 nanometer. 1 nanometer. So, almost reaching close where amorphous phase will exist, right. Now, these are all crystalline ferrite. So, I have cobalt oxide and Fe2O3, here I have barium oxide Fe2O3, here it is Fe3O4 and so on. Now, particle diameter if it decreases, then the corrosivity is going to improve. So, it is very clear. So, like if we can reach to 100 nanometer in case of cobalt ferrite, we can always go up to a very high value, and you can see here the plot in the top side of the plot, it is 10 to the power 3 ampere meter, okay, which basically means that this is the whole range of hard magnet actually. So, the corrosivity value, that is a characteristic for the hard magnet which has a greater than 10 to the power 3 ampere meter. So, up to let us say in case of cobalt ferrite, when we reaches close to 10 nanometer, we can go up to the maximum value, but if we further decrease the grain size, then there will be again a decrease in the corrosivity, and these are the phenomena that are linked with the quantum confinement, because if we go to very small particle size, then electrons in a quantum dots, they are very much confined. So, that restrict the improvement of the hard magnetic properties linked with that. Now, if we go for this look at the application side of such hard magnetic material, the first example that comes that the high energy product. Okay. So, like MRI and magnetic resonance imaging. So, where we need hard magnetic material. On the other hand, we use everybody like a personal computer, we have a hard magnetic drive where memories and the 1 0 they are all stored. And so, here I show you another example of such hard magnetic microstructure with a 50 nanometer size or less than that, you have some grain size. Okay. So, this is a typical cobalt chromium alloy with a two phase microstructure. So, the boundary here, the grain is cobalt chromium and the matrix region is another oxide grain boundary phase. Okay. So, that is a lighter region. So, here these are the like a granular type of microstructure, and we basically pass such a writing head on this kind of magnet and orient these magnetic spins, which is used as a recording medium. So, this is just a schematic diagram of the hard disk drive that employs some perpendicular magnetic recording medium and also shows such kind of inducting write and magnetorestrictive reading heads. So, one is the reading head, another one is the writing head. So, we provide signal which one to align what direction. So, here you can see both the domains are aligned in a particular direction. It basically memorizes whether 1 and 0 and so on. So, magnetic powder that can be aligned using this hard magnet, let us say proximity sensors that is used in a car and so on, we can use let us say in case of motors, actuator, also in microphone, generator we can use, and also for magnetic levitation. This is a new technology that a train is levitated in a magnetic field. So, here this is called as maglev. So, these are also very important in case of bearing, coupling and so on, and let us say some of the switchable clamp, brakes, metal separation. For all these purpose, let us say for high energy product, let us say these hard magnetic materials are very much important, and we should and people should develop the more and more harder magnet along this direction by keeping all the fundamentals into mind. So, we have seen many different types of application including the beam generation and so on. So, another very important magnetic application is for some cancer therapy. So, hyperthermia, that is a application we talk about where we need some required characteristic of material. So, in that case the particle that are super paramagnetic that avoid clustering of the particle in a blood vessel and significant amount that losses in a external magnetic field by altering let us say AC field. So, here these are some typical example like conventional Fe3O4 that has 15 nanometer grain size, manganese ferrite, cobalt ferrite and manganese cobalt ferrite together, and we have some specific loss power that can reach up to here, whereas for conventional ferrite it is relatively low. So, magnetically hard and soft exchange coupling, and let us say here hard magnetic is like cobalt ferrite or let us say manganese ferrite act as a soft. So, we can couple these together and to make a specific loss power, let us say these are some determined at 400 kilohertz at different particle diameter within the range of 10 to 15 nanometer that I have mentioned you. So, with a very small particle size we can reach to a very hard magnetic properties with a very extremal losses and magnetic exchange coupling in a coated particle. So, these are some of the very large and wide application areas of this hard magnetic material. With this we complete our discussion today, and we will start with again soft magnetic material discussion in the next class. Thank you.